Welcome to this lesson on buffers. Today, we'll explore one of the most important concepts in acid-base chemistry. Solutions that resist changes in pH buffers play a crucial role in maintaining stability in both chemical and biological systems. Understanding how buffers work will help you appreciate their significance in everything from human blood to laboratory experiments. A buffer is a special type of solution that resists changes in pH when small amounts of acid or base are added to it. The key word here is resists. Buffers don't completely prevent pH changes, but they minimize them significantly. This ability to maintain a relatively constant pH makes buffers essential for biological processes and chemical reactions that require stable pH conditions. Every buffer system contains two key components working together. The first component is a weak acid, which neutralizes any base that's added to the solution. The second component is the conjugate base of that weak acid, which neutralizes any acid that's added. These two components work as a team. When one reacts with added acid or base, the other remains ready to handle the opposite disturbance. Let's look at a common buffer system, the acetic acid buffer. This buffer consists of acetic acid, represented by the formula CH3COOH, as the weak acid component. Its conjugate base is the acetate ion, written as CH3COO-. This buffer system is widely used in laboratories and demonstrates perfectly how a weak acid and its conjugate base work together to maintain pH stability. Buffers work through a beautiful chemical balance. When you add acid, which releases H+ ions, the conjugate base in the buffer neutralizes it. For example, acetate ion reacts with H+ to form acetic acid. Conversely, when you add a base like OH-, the weak acid component neutralizes it. Acetic acid reacts with OH- to form acetate ion and water. This way, the buffer handles disturbances from either direction. The Henderson-Hasselbalch equation is the mathematical tool we use to calculate the pH of a buffer solution. The equation states that pH equals pK plus the logarithm of the ratio of conjugate base concentration to weak acid concentration. This equation shows us that buffer pH depends on two factors, the pK of the weak acid and the ratio of the two buffer components. It's an essential formula for anyone working with buffers. Buffer capacity refers to how much acid or base a buffer can neutralize before its pH starts to change significantly. Think of it as the buffer's strength or endurance. Two factors determine buffer capacity. First, higher concentrations of the buffer components mean greater capacity, more molecules available to neutralize added acid or base. Second, buffers work most effectively when the concentrations of the weak acid and conjugate base are equal. Every buffer has an effective range where it works best. This range follows a simple rule: pH equals pK plus or minus 1. In other words, a buffer is most effective within 1 pH unit above or below its pK value. Outside this range, the buffer loses its effectiveness because the ratio of acid to base becomes too unbalanced. This is why choosing the right buffer for your target pH is crucial. Buffers are absolutely essential in living systems. The most critical example is the blood pH buffer, which consists of carbonic acid and bicarbonate ion. This system maintains blood pH at 7.4, which is vital for survival. Another important biological buffer is the phosphate buffer system, made of H2PO4- and HPO42-. This buffer is particularly important in intracellular fluids, helping maintain proper pH inside cells. Let's recap the essential points about buffers. First, buffers resist pH changes through the combined action of a weak acid and its conjugate base pair. Second, we can calculate buffer pH using the Henderson-Hasselbalch equation. Third, buffer capacity depends on the concentration of buffer components and their ratio, with equal concentrations providing maximum capacity. Finally, biological systems rely heavily on buffers for maintaining the stable pH conditions necessary for life. Understanding buffers gives you insight into both chemistry and biology.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.